Good evening. I'd like to start by thanking Remake Labs for sponsoring this Tech Talk. My name is Meredith Britt, and tonight I'll be talking with you about observability and microservices and event-driven architectures and how to achieve better visibility into your system through distributed tracing. To inform our deep dive into this topic, we'll begin with an overview of the microservices pattern and how its loose coupling and reliance on communication allow for more independence between services. We'll then take a look at two key concepts that help us maintain and improve system performance, monitoring and observability, and how they are especially helpful in distributed systems. Then we'll home in on one of the three pillars of observability, distributed tracing. We'll learn why it's so handy for pinpointing where we can improve our system. Lastly, we'll get a hands-on look at how distributed tracing is applied in a microservices architecture. Before we drill down, let's first build some common ground, starting with a microservices pattern. Microservices architectures loosely couple services to allow core functions of an application to exist independently. But what does this mean exactly? I had some glaring questions milling about in my head when first exposed to this pattern, like, what exactly is a service? What does it mean to be loosely coupled? And how do these services communicate exactly? A service often serves a single core function of an application, as shown here in our simple diagram. A food delivery app would likely be made up of services that represent core activities of the business: ordering food, making food, and delivering food. Each service has its own business logic and its own store of data to support its processing. There are also several common utilities that an application often employs, like an API gateway to route client requests, load balancers to distribute traffic, monitoring for system performance and business analytics, among others. The core functions and utility services all operate independently, meaning they can be added, maintained, or removed from the system with minimal effect on other services. This independence allows for different teams or even third-party providers to manage particular services. Each team or vendor can work in their preferred tech stacks while not interfering with other services. This separation is achieved by enabling these services to communicate with each other, passing data back and forth. In our current system, the data is passed through synchronous communication. The API gateway calls a service through an HTTP or gRPC request. In this system, the front-end application would start off the chain of requests and responses. An HTTP request would be sent to the order service. Once the order has been processed and stored, the order service sends a response back to the API gateway, which sends its next request to the kitchen service, letting kitchen staff know an order has been placed, along with order details, and so on. This synchronous communication binds the system together more tightly, meaning the services, while more loosely coupled than in a monolithic architecture, still have some dependence on each other and communicate more directly. In this system, if a service becomes unavailable or if processing speeds vary from service to service, there is potential for data to be lost or received out of order. Notice in our diagram how the kitchen service has a slower processing speed than our order service, and therefore isn't able to receive the request for order number 2, so the order times out. This is why message brokers are often utilized in a distributed system. They allow services to communicate asynchronously through a queue. When one service emits a message, it's stored in a queue until the receiving service is ready to process it. The queue ensures messages are processed in the right order and data is not lost. Message brokers offer greater flexibility in how services in the system communicate. Because the service originating the message and the receiving service don't have to know about each other, the communication patterns that message brokers implement are more varied. For example, the message broker could set up point-to-point messages between two services, but with the added value of a queue, as shown in this diagram. Or it could utilize the publisher-subscriber pattern, and multiple services would process the same message. Looking back to our original system for our food delivery application, we've now added asynchronous communication into our architecture. We've maintained one path that relies on HTTP requests. Our user profile service updates the user's information and sends a synchronous response to the user confirming the updates. All other network communication is being routed through a message broker. So our services can flexibly use different communication patterns and are more loosely coupled because the services do not have to know about each other to communicate. Now, before we move on to discuss monitoring and observability, I want to make a point about some characteristics that HTTP and gRPC requests and messaging have in common. 1, they are prompted by some kind of action. 2, they often carry a payload with data for the service to act on. And 3, they're accompanied by metadata to help process the request or message. Let's hold on to the ideas of loose coupling and communication between services as we shift gears to discuss monitoring and observability. Remember the helpful gains that came with reduced coupling, more independent operation, ease of incorporating different teams or third-party providers, reliable asynchronous processing of data. These benefits come at a cost to our inherent visibility into the system. Or to put it more simply, what is going where and when? The likelihood of sussing out the answers to these questions in our example architecture is pretty high. We don't have a ton of services to keep track of, but what if your architecture looked like Netflix's? Even with dozens of services, understanding what's going on in your system will be complicated. What if you have hundreds? Developers rely on monitoring and observability tools to better understand what's happening in such a complicated system. Service monitoring, therefore, is a core piece of system design. So let's dig in. Even in the simplest of applications, you've probably practiced monitoring and observability yourself. When you monitor, you watch key indicators to assess overall performance. If you've ever checked to make sure your application is running, you are doing a basic form of monitoring. We can also monitor our applications for key performance indicators of the business, the end user's experience, or performance on service level agreements between teams or contractors. Another area that provides a vital bird's eye view is your compute infrastructure, namely CPU, memory, and disk usage, to ensure you have sufficient compute power and space. You can monitor your dependencies, such as your cloud services, payment processing systems, or external APIs. And lastly, your network infrastructure. That's where we'll focus as we move into our next concept. Observability allows us to understand the internal state of a system by analyzing the data it generates. While monitoring focuses on overall performance, observability provides context. Traditionally, it's achieved through 3 pillars: logs, metrics, and traces. Modern observability also includes user experience and security. For our conversation, we'll focus on the first 3 pillars. Logs are text-based records of events that occur while an application is running. It's important in microservices architectures to have a centralized collection of logs to help determine the root cause of problems. Metrics are numerical assessments of a system that allow you to view aggregated data in real time or identify trends over time. Metrics are meant to be simple so that developers can quickly interpret them and easily set up alerts if they reach critical highs or lows. Distributed tracing is the process of connecting a single request through multiple calls within and across microservices. With traces, you can track a request from the application's UI as it moves through a network of services. Distributed tracing makes pinpointing the root causes of latency and failures in a system much more transparent. With tracing, a developer can easily follow a single request through an architecture like Netflix's. In systems that don't utilize distributed tracing, the process for developers can look something like this. The engineer in blue pants sees a change in metrics and perhaps has a laundry list of ideas of what could be causing the change. They run queries on their logs until they find something that signals to them the root cause of the issue. If they're lucky, this happens early. Sometimes the answer isn't totally clear. The engineer in red on another team might come to a different conclusion. And thus multiple teams have competing understandings of what's going on and who needs to put work in to address the issue. This is where distributed tracing comes in. With a trace, developers can quickly detect the root cause, reducing the overall time it takes to discover and repair the problem. A quick disclaimer, metrics and logs are 2 important pillars of observability, and developers should work to achieve whatever level of observability they can, even incrementally. So go ahead and implement logs and metrics if that's doable first. Don't wait for distributed tracing. With that being said, let's take a closer look at how distributed tracing works. Remember our food ordering app from earlier? Recall that it communicates through HTTP requests and messaging. With distributed tracing, we attach a trace ID and operation ID to the header in each HTTP request or the metadata of each message. I like to think of it like a passport. The trace ID is your own unique passport number issued only to you. Let's say you're going on a big trip and will visit multiple countries on your journey. For each country you go to, you collect stamps, which are like the operation IDs. By the end of your journey, you have a record of all the countries you've been to and when you entered and left each one. The process of collecting operations IDs as a call moves through the system is called context propagation. Imagine each request has its own passport. As it moves through the system, the request collects each operation ID, as well as the service's name, start and end timestamps, and other relevant metadata. Each activity that is triggered as a request moves through the system is called a span. Each span is sent to a collector that buffers the spans and groups them by trace ID, like a record of the itinerary of your trip. And here we can watch our request take its trip through each service, through load balancers, through our message broker. And each span is sent to our collector with the trace ID that unites all of the different spans. Keep in mind, the route a request or message takes can often vary a lot more than in our food delivery app, as seen in this trace of a single request through Uber's system. All the spans are sent to an observability backend, which knits the spans back together into a full trace and shows how the request moves from service to service. Now, instead of just looking at metrics and querying logs, we can visualize exactly the services a request moves through and how long each service takes to perform its processing of the request. We can pinpoint services that are causing latency, or if a service is failing altogether, we could see where the request is stopping in the system. We've just touched the surface of distributed tracing and observability. So before I go, for anyone interested in this topic, I'd suggest you check out OpenTelemetry. It's a cross-industry effort to standardize how applications, data collectors, and telemetry tools interface. It's an open source framework and toolkit that provides instrumentation to collect observability data and can be used with a wide variety of open source and proprietary observability backends like Jaeger and Prometheus. Thanks for your time tonight. If you'd like to talk about observability, distributed tracing, or anything else, please feel free to reach out on LinkedIn. And here's my GitHub. Here are my works cited. And thanks again to Remake Labs.